So this week I'll be showing you two problems and the solutions to both of them. Basically, the point is to show my thought process. So I haven't written up a solution for either of these. So I'll be doing it kind of on the spot. This first one is going to be kind of just like a logical question. So these are the kind of questions that you're going to work on this week. And then the other one is going to be a proof that by the end of this class you'll be able to do, like by the end of the semester, but maybe right now you wouldn't be able to do this on your own, and maybe it's a little bit confusing, but it'll be helpful to see something in action, hopefully. Okay, so here's the question. There is a school with 1,000 students and 1,000 lockers. On the first day of term, the principal asks the first student to go along and open every single locker. He asks the second to go to every second locker and close it. The third to go to every third locker and close it if it is open, or open it if it is closed. The fourth to go to the fourth locker, and so on. The process is completed with the 1,000th student. How many lockers are open at the end? Okay. So I'm a very visual person, so I like to draw pictures. I'm not gonna write 1,000 lockers, but let's just do 4, let's say, at the start. Okay, so the first student goes along, opens all of them. Okay, so from the first student, maybe open. Okay, So the second student is going to come along and they're going to skip the first one. Okay, so the first one is now fixed forever because none of the students are ever even going to interact with the first one again. Okay, so the first one is stuck forever now. And so this student is going to go along and close. Maybe I'll do an X. We could play tic-tac-toe. Okay, so now, but every other, right? Okay, interesting. So now the third student, let's do the third student in green. The third student isn't going to interact with the first, we already talked about that, or the second locker. So now the first and the second locker are both fixed. So the third student, their assignment is to just do the opposite. Every locker that they come across, they have to do something. So if it's open, they close it. If it's closed, they open it. So the first one they come to is this one, okay? So what they're going to do is they're going to close it. So, well, yeah, let's do a different color. So they're going to close it. Okay, they're going to ignore this one, but that doesn't mean that that one's fixed forever. Okay, we'll see that in a second. So now they're going to go, so let's extend my drawing a little bit. That'll help. Okay, so let's see. So the next one that they're going to hit is the sixth one. So let's see what happens with the sixth one. So 1, 2, 3, 4, 5, 6. Let's just do 7 for kicks and giggles. Okay, so our first student went through and opened all of them. Our second student went in and closed every other. Okay. So our third student, so it went and it closed the third one, and then the student comes to the sixth one and it has to do something. So it's closed, so they're going to open it. So they open it. And then they go on and on and on and on. Okay. So one thing that we can notice right away, the first one, that pattern is simple. They just opened all of them. Whether they were closed or open to start with, they just went across and opened all of them. The second student, we can notice, wait a second, if they open every other, that means that they're only open the even numbered lockers. Okay, so then when it comes to the third person, their pattern is that they only go in multiples of 3, but every other multiple of 3 is going to be even. So you think 3, 6, that's even. 9, that's odd. 12, that's even, so on and so forth. Okay, so every other, they start with closing one, then they're going to open one, then they're going to close one, then they're going to open one, etc., etc. So now let's do another student. I don't know what color to pick. Let's do orange. That sounds like fun. Okay, so now we're going to take, so our fourth student is only going to interact with, the first one's going to interact with is the fourth locker. So once again, these are fixed. The 1 through 3, they're fixed. Okay. So the fourth one, so everyone after the third one is just going to do something to the locker. So if the locker is closed, they're going to open it. If it's open, they're going to close it. So the fourth student is going to start by opening the fourth locker. And then the eighth locker, we can guess what's going to happen to it because, well, we don't have to guess. We know what's going to happen to it because we know that the second student closed that locker because 8 is even. But 8 is not divisible by 3, so the third student didn't do anything to it. So the fourth student is actually going to open that locker. Okay, so are you kind of following that? So here, let's actually write it out. So first student, here it might be kind of hard to read my writing if I write like that. So let's just do it like this. First student opens all. Okay, second closes evens. So a quick definition that you'll learn in the class is an even number is any number that can be written as 2 times n, where n is an integer or a whole number. So 0, 1, 2, 3, but also -1, -2, -3. So -4 is an even number. Okay, so this is the symbol for the integers. That just means, so ... just indicates it's going on forever and ever and ever and ever. Okay, and you'll learn this formally later. So if you don't remember it, that's okay. We'll talk about it again in more detail. And then an odd number is anything that's one off from an even number. Okay, so if you notice, every even number, you can just add 1 or subtract 1 and you get an odd number. So that's basically kind of what we say. So it can look like this. You can write any odd number like that, like an even number plus 1, or you could say -1. Okay. All right, so the second student closes evens. Third student, okay. So it's going to open evens that are multiples of 3 and close odds that are multiples of 3. So 4 might look a little strange to us right now, okay? Because we talked about 4 and we talked about 8. So any multiple of 4, that's always going to be even, okay? Because 4 is an even number. So, and we'll learn that later actually, that multiples, if you multiply 2 even numbers, you get an even number. Okay. So let's think about what happens at 12. So at 4, the student is opening it. At 8, the student is opening it. What happens at 12? Well, funny we should ask that. We know that the first student opens it, the second student closes it, but does the third student interact with 12? Is 12 divisible by 3? Yes, it is. And the third student opens even numbers that are multiples of 3. So 12 is a multiple of 3, and it's even. So the third student is going to open it. So the fourth student's actually going to close it. Okay, so how we can define the fourth student. And so now I'm just going to write these things that we know under the assumption that these numbers are multiples of what number the student is. Okay, so I'm going to say that for it opens. So here, let's write it like this. So it closes multiples of 3 and opens all others. Under the assumption that all the numbers I'm talking about are multiples of 4. Okay, so why do I know that I can do this, this generalization? Well, the argument that we just talked about. We know that the second student is going to close all even numbered lockers, and we know that the third student is going to open any even numbered lockers that are divisible by 3. So if 4 comes across something that's divisible by 3, that is going to be an open locker. So the fourth student has to do something, well, they're going to have to close it. But any other locker that they find that's not divisible by 3 was closed by the second student, was closed by the second student, so the fourth student's going to open it. Woo, all right, yeah, this is crazy. So a lot of stuff is happening. Okay, and I'm not exactly sure how we're going to solve it yet. But one thing that we do know is that once you get to the fifth student, then lockers 1 through 4 are all going to be fixed. So to me, my thought is we're going to want to figure out what each of these columns look like by the time you get to that numbered student. Because then after that student, it's going to be fixed. Okay, so let's think about how we can do that. So I'm just going to label first student, second student, third student, fourth student. Okay, so now let me also make lines. Okay, so what can we recognize with who has what marked off? Well, 1 is only divisible by 1. 2 is divisible by 1 and by 2. 3 is divisible by only 1 and 3 because it's a prime number. So that's another definition we'll go more into later. 4, though, is divisible by 1, 2, and 4. Okay, and so 5 is also prime, so it's only divisible by 1 and 5 itself. 6, if we went on to 6 students, we would see that the only next row that would be marked off would be 6. Okay, so 6 is divisible by 1, 2, 3, and 6. Okay, and so this, if it didn't jump out to you because you didn't draw something or something like that, maybe you would have noticed it when you started writing these things out. And so it might look kind of silly that I'm writing these things out. But it really does help to start seeing the patterns if you start rewriting what you're seeing. Because here we keep talking about, oh, if it's a multiple of 3, if it's a multiple of 4. So both those rows would be ticked off either by an X or a 0. Know however many divisors each number has, I can just alternate that. Okay, so maybe let's come up with the solution of, okay, so 1 means, how about -1 means open, and 1 means closed. Okay. So some variables. N blocker is -1 to the, let's say, m, okay? So meaning it's either open or closed, right? Where m is the number of divisors of n, okay? And so let's double check our equation on what we've already figured out. So for 1 only has one divisor. So -1 to the 1, that's -1. So that means it's open. Yep, that's what we got. Okay, 2. We got that 2 is closed. -1 to the 2, that's 1. So that means it's closed. Okay, so now we have our part of our solution. After a lot of thought that I didn't want to record, just to save you time, I don't want you to sit there watching me, him and him. Okay, here's the pattern that I found. So we were right with this, but what do we notice? Let's reread the question. I should have taken my own advice. This is like the biggest piece of advice that I would give anyone at any level of math that they're at, from elementary school up to graduate student, is if you get stuck, reread the question and then talk about what it is that you want, okay? So after rereading the question, I remembered I just need to know how many are open. So I need to know what numbers are going to give me negative. Well, to be negative, its number of divisors needs to be odd. Well, when does that happen? That happens when there's not, so let's skip to 6. Let's pretend like, oh, I went to 6 or whatever. What do I want? Green, we already did purple. Let's do purple. So let's say 6 is down here. They would go and they would close that. So number 5 would close 5 too. Let's, okay, so what do we have in common with the ones that are closed? Well, let's just make some more simple observations. We don't have to make things hard for ourselves, okay? So for 1, we only have one divisor. For 2, we had 2, so this one canceled that one. 3, similarly, they canceled each other out. 4, we didn't have things cancel each other out to get it closed again. 5, they cancel each other out. 6, so this, let's say that open cancels with this one, and let's say this open cancels with that one. Okay, so let's think about where I had those cancellations happening. Sorry, let me move this so I can undo. The other way that I can think about it, and I did that in a specific way, 6 times 1 equals 6. 2 times 3 equals 6. And so where am I getting these numbers? I'm getting them from which student did it, okay? And I'm multiplying those students' numbers together. So 3 times 1 equals 3. But what's special about 4? Well, 1 times 4 equals 4, but those don't cancel each other out because this middle number, it's 2 times 2 is 4. So we want to take numbers that are squares. Okay, so numbers that are squares end up having an odd number of divisors. So let's take another example. Let's say 16. Okay, let's go down here. So we have the number 16. So 1 is going to open it. 2 is going to close it because it's divisible by 2. Is it divisible by 3? No, so 3 is going to skip it. 4, it is divisible by 4. Actually, that's its square, so that's probably where some magic's happening. But now we know at this point, so this is something that maybe you talked about in other math classes, this is like our turning point, is at 4. Because you're not going to have like 5 times something higher than 5 end up also being 16 if 4 times 4 is 16, right? Because if 1 goes up, so you have 4 times 4, okay? So if we move 4 up to 8, we can't also move this one up, right? We have to move it down to 2. So this is kind of like our turning point. So after this, every other number that I list is going to have to be multiplied by the ones that I've already listed. So this one is 2, remember, and this one is 1. So 2 gets matched up with 8. Okay, so I know 8 and 16. Maybe this is a better way to write it, is I'll write out the numbers that I know are multiples of 16 first, and then do this. Okay, so 1 is a multiple of 16, we opened it. 2, we closed it. 4, we opened it. But it's 4 times 4. So 4 doesn't get a counterpart. Everybody else gets a counterpart that it cancels with. So 8 we close, and 16 we open. How cool is that? Okay. So see what I'm talking about? So 1 would cancel with 16, but it doesn't, right? Because we have this 4 here who doesn't cancel with anybody. So let's do another example that is not a square. 15. Let's do 15. Okay, so 15, its multiples are 1, 3, 5, and 15. Okay, so 1 we open. 3 we close. 5 we open it again. 15 we close. So this one we do have some cancellation within the multiples. So 1 times 15 is 15, and they cancel each other out. 3 times 5, they multiply to 15, and they cancel each other out. 1 is closed, 1 is open. But over here, 1 times 16, that's 16, but they don't cancel each other out. They're both open. Okay, and that's because of the magic of the number 4. So now all we need to do is figure out how many squares we have less than 1,000. What do we do? So we have 1, 4. So let's do it like this: 1 squared, 2 squared, 3 squared, 4 squared. Well, let's skip to a really big one. Let's say 30 squared, 900. 31 squared. It's just going to be 960. Jesus. Let me tell you, one of my professors in undergrad said the more higher level math you learn, the more lower level math you forget. And I have found that to be true. Okay, so we get that. 32 squared. Oh boy. I'm not going to embarrass myself. I'm just going to type it in. Ooh, okay, so this is 1,024. So this one we're not going to count in our count. And what's great about this is by the way that I wrote this, I'm already counting how many squares we have, okay? Because I'm doing it by who we're squaring. So I know that we have 31 squares, which means we have 31 lockers open. Excellent.